Hello, my name is Dan Scales and I'm a software engineer at Google. Today I'm going to be talking about Go's defer statement. I'll talk first about the semantics of defer and contrast it with related features in other programming languages. But then I'll mainly focus on how defer is implemented in the Go compiler and runtime, and describe how we made defer run very efficiently in Go 1.14. Though it's probably well known to most of you, let me first define the defer statement. A defer statement is a defer keyword followed by a function or method call. The function pointer and any arguments are evaluated immediately, but the function or method call is specifically deferred to run when the function finishes. The important thing is that the call is guaranteed to be executed for any return from the function, and is also guaranteed to be called if the function is exited because of a panic. Of course, this makes defer very useful for cleaning up resources like mutexes that have been acquired, or files that have been opened. And as I mentioned on this slide, defer is a new language construct invented during the development of Go. So here in this slide, we have an example of the use of defer in a command line utility. This function will either open a file or use standard in as input based on the use standard in argument. If a file is open, we want to make sure that the file is closed no matter how the function is exited. So, as you can see, if useStandardIn is false, the file specified by file name is opened, and then we use the defer to express that f should be closed no matter how the function exits, whether the function completes without an error, returns early because of an error, or exits because of a panic. It's nice that defer can be called anywhere, even in a conditional clause, and that it clearly expresses exactly what needs to be cleaned up. Now, there have been concerns about the overhead of defer statements. And in fact, as shown in this check-in to the Go repository, developers have sometimes removed defer statements from critical functions in order to improve performance. There have been a number of these changes in the Go standard library, and I'm sure in other popular Go applications. But we definitely don't want people avoiding defer for performance reasons. So, our goal for Go 1.14 was to make defer overhead low enough that developers can always use defer whenever it makes sense. We want to eliminate the common belief that defers can be expensive. So, the plan for the rest of the talk is as follows. I'll first describe some related features in other languages and compare with defer. Then I'll describe the implementation of defer as of Go 1.13. Then I'll describe the optimization for defer that we did in Go 1.14 that greatly reduced the overhead in the common case. Finally, I'll describe some performance results and future optimizations. If we look at other popular programming languages, there are related constructs that also try to ensure that code will be executed no matter how a function or a block is exited. C++ has a paradigm called RAll, which stands for Resource Acquisition is Initialization. The idea here is that the acquisition of a resource, such as a lock or an open file, can be associated with the declaration and initialization of a variable in a certain scope. Acquiring that resource can be part of the constructor of the variable, with the resource being specified as an argument to the constructor. C++ guarantees that the destructor method for an object will be called when the scope of the variable ends. And of course, we can release or clean up the resource in the destructor. Very importantly, like the defer statement, C++ guarantees that the destructor will be called even if there's an exception. So, in the declaration I display on the slide, the variable fs is declared as type OFStream. But also, since the file name string is specified as a constructor argument, the file example.txt is opened and used to create the file stream. When the destructor is called at the end of the block, the file will automatically be closed. And this will happen regardless of whether the block is exited normally or via an exception. Now, one thing to note is that RAI is statically analyzable. The compiler knows exactly what destructors to call at the end of each block. So the compiler can make the code very efficient in the normal case. However, RAI really only makes sense for languages that are not garbage collected, since only for those languages can an object be completely tied to a variable and guaranteed to be destroyed at the end of the variable's scope. Another way to express the idea of guaranteed cleanup is the try finally statement. As you know, the block following the try keyword is first executed, and then the code following the finally keyword is guaranteed to run, regardless of whether the try block finished normally or had an exception. This approach works for garbage collected languages, and so it's used for Java, JavaScript, and Python, among other languages. Like RAI, the try finally statement is static and fully analyzable by the compiler. The compiler knows exactly the code from the try finally block that must be run, regardless of whether the try block finishes normally or because of an exception. And lastly, I think it's interesting to remember that there's a thing called a finalizer in Go, and compare it with defer and RAII. A finalizer in Go is a function you can set via runtime.setFinalizer, which is guaranteed to be run before an object is garbage collected. So in some sense, it's similar to RAII, and C++ is guaranteed that the destructor of an object will be called before the object is deallocated at the end of the block. But remember, there's no guarantee that on when an object in Go will be garbage collected. There's definitely no guarantee that an object will be garbage collected before the program exits or if there's a panic. So finalizers in Go are rarely used and are only for cases where we want to prevent slow leaks of resources that are tied to long-lived garbage collected objects. So now that we've described some of the related features in other languages, we can discuss some of the advantages of defer and compare with those other features. One aspect of all these features is that they enhance the maintainability of code. They guarantee some cleanup code will run at function exit, no matter if more function returns are added or moved around or removed. This is especially important in the case of error returns, which may not happen very often during normal execution and can be hard to test. Another aspect of all these features is that they enhance robustness to bugs or very unusual cases, in that they guarantee the cleanup will also happen in the case of panics or exceptions. This guarantee is important for things like long-running web servers, which should continue running even if there is an exception while handling an individual request. We want to abort the thread that had the panic and continue, but only after cleaning up all the resources held by that thread, including, for example, locks that it was holding. Now, this is definitely a matter of taste, but one possible advantage of defer over the related language features is in the area of clarity. I personally think it really adds to the clarity and maintainability of code that the cleanup of a resource is expressed via defer right near where the resource is created or acquired or opened. In contrast, in try finally, the cleanup in the finally clause can be quite far away from the relevant code. On the other hand, you might say that defer can be a bit repetitive compared to C++'s approach, where the cleanup is implicit in the destructor. Finally, I don't have a single word for it, but defer is very good at expressing conditional cleanup, since it's a simple statement that can appear anywhere in a function, including inside if statements. None of the other related languages have a great way to express this conditional cleanup. Now, however, that does bring us to one of the aspects of defer that could be considered a disadvantage and that complicates the implementation. Unlike most of the related features, defer is completely dynamic. It can be called inside an if statement, as we said, and it can also be called inside a loop. Because of these defer dynamic statements cases, especially the case of being called inside a loop, defer must be in general implemented with the help of the Go runtime. The case of defer in a loop can be expensive to handle and may require allocating heap memory. But the common simple cases of defer are fully analyzable by the compiler, and we would like to make these cases as efficient as C++ RAII. And in fact, that was our goal with the optimization in Go 1.14. Before we get to the optimizations in Go 1.14, let's talk about the implementation as of Go 1.13. On the left, we have a small function with a defer statement, and on the right, we have roughly the way the function is rewritten by the compiler to implement defer. At each defer statement, a defer record is allocated, and the function pointer and args are evaluated and stored in the defer record. Then runtime.deferProc is called to finish initializing the defer record and link it into the defer chain, which I'll talk about in the next slide. At every function exit, runtime.deferReturn is called to process the active defers. The return value of 1 from deferproc here is only used when there is a recover from a panic, and it's a way to re-enter the function when the panic is recovered. I'll give a little more detail on that in a couple slides. So as you can see, in Go 113, we're making a number of calls to the Go runtime to implement any defer. Now, what is a defer chain? What is the defer chain? It's a linked list maintained in the Go runtime of the currently active defer records. Each defer record contains the function pointer and arguments for a defer call, and a pointer to the associated stack frame. So in the figure on the right, we show a defer chain that has 1 active record for main and 2 active records for the function g. When possible, defer records are allocated on the stack, but they must be on the heap if the defer is in a loop. As we mentioned, runtime.deferproc initializes defer records and adds them to the end of the chain. And a function exits runtime.deferReturn processes defer records in a last in, first out order from the defer chain, but only for the current stack frame, so just for the current function invocation. Now, one of the complexities of defer statements is how they are handled during the processing of a panic. The handler of panics is runtime.gopanic, and gopanic processes defer records in a last in, first out order as well. It continues making the defer calls associated with each defer record until it has handled all defer records, or until a defer function does a successful recover. If a successful recover occurs, the runtime returns to the deferproc whose function did the recover with a return value of 1. So here again we show the generated code, and we're pointing to the point where the runtime returns with a value of 1. This causes the program to run the code snippet that calls defer return to process any remaining defers in the function, and then do a normal return to the calling function, thus completing the successful recovery. Of course, this is just for the purposes of illustration, since a deferred unlock is not likely to be doing a recover. So that was a quick description of how defers are implemented as of Go 113. But for Go 114, we'll want to make deferred calls less expensive for the simple cases. We'd like to get rid of all the runtime overhead. This is especially important when defers are used to defer inexpensive calls, such as mutex unlocks. And now we'll only do this optimization for functions that have defers, but none of the defers occur in a loop. The idea is that at defer statements, the compiler generates code to evaluate the function pointer and arguments, as usual, but stores these into unique stack slots instead of using a defer record. In addition, the generated code updates a bit mask called deferBits, indicating which defer was activated. At every exit from the function, the compiler generates code to execute each active defer call in reverse order. The generated code specifically checks deferBits to see what defers were activated. I'll show an example of this in the next slide. So, in normal execution, no defer record is created, and there are no calls into the runtime. Our term for defers compiled in this way is open-coded defers, which means that we have directly generated the code that handles the defer in the normal case. So here is an example of the rough code that the compiler generates for 2 open-coded defers. In deferBits, the lowest order bit represents the first defer, and the next lowest bit represents the second defer, and so on. So as I've shown here in bold, defer f1 of a is transformed into code that evaluates f1 and a, stores these values into temp f1 and temp a on the stack, and sets the lowest bit of deferBits to 1. Similar code is generated for defer f2 of b, which is executed only conditionally. f2 and b are evaluated and stored into the appropriate stack slots, and deferBits is updated. Then, at each exit of the function, the compiler generates code, which I've shown in bold, to test each of the relevant bits of deferBits in reverse order and make the appropriate deferred call if that bit is set. And just as a reminder, deferBits and all the temp variables are extra stack slots allocated in the stack frame of G. In addition, this is in addition to the local variables and arguments that are already there. So in this slide, here are just a few more details on the compilation of open-coded defers. It's important to note that the defer arguments must be forced to be stored on the stack, not just kept in registers, since these arguments must be accessible in case there's a panic. Similarly, all updates to deferBits must be explicitly stored on the stack. Although the exit code in the previous example looked complicated, all the checks on deferBits will be optimized away if none of the defers are conditional, thus making the exit code much simpler. Currently, for the simplest code, deferBits is just a byte, so 8 bits, but that could be increased if needed. So currently, we actually revert to using non-open-coded defers for functions that have more than 8 defer statements. The code generation changes for open-coded defers are fairly simple, and the resulting code is very efficient. But the trade-off is that panic processing becomes somewhat more complex because we haven't created any defer records. The set of active defers is encoded in relevant stack slots. So for open-coded defers, we need to make information available to the runtime about which functions use open-coded defers, and for these functions, where the information about the defers are stored in the stack frame. Funcdata is the standard way to store extra information in the Go binary about individual functions. It's essentially a symbol that can be accessed by the Go runtime. So we generate funcdata for each function with open-coded defers that describes the location of all the relevant stack slots, including the location of deferBits and all the arguments of the defer calls. And this is a bit of a detail, but in addition, in order to handle recovers, we need to add an extra stub of code for each function with open-coded defers. This stub allows us to call defer return in the right context whenever there's a recover, to finish any remaining defer calls, and then to return normally to the calling function. So now in this figure, we show a stack on the left and part of the Go binary on the right. In our last example, we had a function G that deferred a call to F1 and maybe to F2. In the stack frame for G, we show the stack slots that are used to store defer bits and the various defer args. And we also show that a panic has happened. In this figure, the stack is growing upwards. So how do we know what defer calls to run when there's a panic? On the right, we show that the binary contains the code for G and also the funcdata for open-coded defers in G, which is labeled g.opendefer. That funcdata contains the offset of the stack slot containing defer bits, the number of defers in the code of G, and the offset for all of the args of each of the defers. It's this information that allows us to grab the right information from the stack to execute a defer call during panic processing. So now we can go through an outline of how we do panic processing when there are open-coded defers. When there is a panic, we first scan the stack. For each frame that uses open-coded defers, we insert a record for that frame in the Go runtime's defer chain in the stack frame order. This allows us to process open-coded and non-open-coded defers in the correct order. We then iterate through the defer chain in the usual last-in, first-out order. We handle records for non-open-coded defers in the same way as before. For each record indicating an open-coded frame, though, we read the funcdata for that function. This allows us to load the defer bits from the stack frame. Based on the defer bits value, we iterate through all the active defers. For each active defer, we use the funcdata to load the appropriate function pointer and args, if any, and make the defer call. Now, if there is a successful recover if a successful recover happens during a defer call in an open-coded frame, we jump directly to the defer return stub in the associated function, which will allow us to process any remaining defers before returning normally to the caller with a successful recovery. So now here we are some quick performance results. Before Go 113, all defer records were allocated on the heap. In Go 113, for defers that were not in loops, the records were allocated on the stack. So there was a performance improvement. And in Go 114, we added open-coded defers. In this chart, we show the total cost of deferring a function call, which includes the overhead at the point of the defer statement to record the defer, and then the cost at the function exit to execute the defer call. And we're showing in the last column the cost to just make the function call itself in the normal way. So now, for a one-argument function, the cost for deferring the function went from 44 nanoseconds in Go 112 to 32 nanoseconds in Go 113 to just 3 nanoseconds for open-coded defers. And that's including the cost of actually doing just the function call, which was 1.7 nanoseconds. So the overhead of the open-coded defer is now much closer to the cost of making the empty function call, instead of being 8 to 18 times higher. With the addition of open-coded defers, we saw some noticeable improvement in some library code that uses defers. This includes invoking cgo callbacks from C back to Go and some crypto code. But you won't necessarily see much improvement in a lot of applications because often defers have already been removed in the case where the defer overhead showed up in profiles. But the problem is that removing defers often hurts maintainability, as we said. The great thing here is that the defer overhead is now low enough that the defers can be added back in where they should be for clarity and maintainability. There's no need to avoid defers, even when the defer call is very inexpensive, such as a mutex unlock. There are several optimizations that can still be done to reduce the cost of defers. First, we can do a little extra work in the compiler and eliminate the deferBits check for any unconditional defer, even if other defers in the function are conditional. We can also do some extra work to use known constant arguments in defer call at exit instead of loading those constants from the defer stack slots. Finally, we might like to have an option to inline deferred calls to known functions or methods. We don't currently do this because inlining precedes defer statement processing in the compiler. So inlining deferred calls would require significant restructuring in the compiler, but it is possible. So in conclusion, I hope that I have increased your appreciation for the defer statement and have shown how it helps improve the maintainability of your code. Defer has been optimized greatly in the last few years. The Go 114 work on open-coded defers has made the common case much faster, as small as a few nanoseconds. The cost is now much closer to the cost of a function call itself and closer to the efficiency of C++'s RAll. So I want to emphasize, as one of the messages from this talk, that defer should now be used whenever it makes sense to make code clearer and more maintainable. Defer should definitely not be avoided for performance reasons. And finally, I'd like to thank all the various members of the Go team at Google for their advice and help in this work. Thank you.